5.2, we're finishing today. This is it. Yeah. So we had looked at properties of multiplication. Let me just remind you of those really quickly. They're all the same properties that we saw for whole numbers, right? Properties of multiplication for integers and whole numbers are identical. It tells us we have closure, so multiplying two of them together gives you another integer. We have commutativity, so we can switch the order around. We have associative, which means we can group them separately in a different way that might be a little bit more helpful to us, generally speaking. The identity property, there's the number 1, and when I multiply by it, it doesn't change anything. The distributive property combines both multiplication with addition and multiplication with subtraction. And then the last one, the zero multiplication property, says when I multiply by 0, it zeroes everything out. So we're going to take a look at 4 of them, and we're going to identify which property is present. So I would like for you to pause. No, I will pause. You don't pause. And I'd like for you to fill in what you think these 4 properties are. Okay, so just list what you think is there. And once you're done listing it, confer with a neighbor, see if you think the same things, and then we'll talk together.
Question mark.
Okay, what did you guys think the first one was? That is closure. So anytime we're talking about it being contained in as an element of the integers, that's a closure property. How about B? That's the zero property. How about C? Distributive. And what do we write down for D? It is commutative. So don't let parentheses just automatically put you in the camp with the distributive property and the associative property. Parentheses also mean multiplication, right? This could just as easily have been written -2.3 and 3.-2, or a good old-fashioned x, right? Back to elementary school kind of stuff too. And it would mean the same thing. So it is commutative. We're just switching the order around. Okay, so we have a few more theorems, and then we're going to move into division. Some of these theorems are just expressing some things that we have done before in a different way. So for every integer a, if we have a -1 times a, it's going to equal -a. Right, that's what we mean when we're talking about that. It's going to change the sign. Theorem 5.7 actually mirrors back to what we did last time with the integer multiplication. It just expresses it differently. It talks about what happens when we have numbers that have negatives with them. So in some sense, when we were talking about over here, that's the one I want, where we identified that A was negative and B was negative, A was certain features about negatives and positives. You can kind of think about this the same way here. This is saying I have -A times B. So if I have that, I could regroup the A and the B together, and then the answer is negative, right? If I have a -A and another negative times it, -B, then those two negatives cancel out. And what's really happening here, just to sort of prove it to you, is that by this definition, right, not definition, but by this theorem right here, if I go the other direction and I started with -A on the right-hand side and I moved back to the left-hand side, I could sort of separate the negative from the A, and I could use these properties of associativity and regroup things, right? So I can group the A and the B together, and then I can put the -1 out in front. Or on the second one, right, I can use the associative. So this is -1 times A and -1 times B, according to the theorem 5.6 above. And then I could pull the two negatives to the front with the commutative property, and I could pull the a and the b to the back, and then negative times negative is a positive using our definition of multiplication that we'd seen last time. So this is just different ways to express some of the same things that we've already encountered. And then the last one is actually the theorem that talks about what happens with subtraction. The reason they're writing this separately than the distributive property for multiplication like I had written it before is because we actually have the ability to have the negatives now, and we didn't exactly have that before. So this is just another statement of the same thing that we had done before. It can actually be proven instead of it being taken as a definition because of the way we're defining negatives. So it's not any new information, it's just presented as a separate theorem, okay? All right. I think division's next, indeed. Notice we're not going to do a whole lot with division. We'll do a little bit. So for all integers a and b, a divided by b is the unique integer c. So in other words, I could write this like this. A divided by b is equal to c if it exists, such that a is equal to b times c. This is how we defined whole number division as well. It's not any different. It's just that it works for division for integers, just like it did for whole numbers. And for the sake of justifying this, let's actually look at a couple of them. So if we did, or like an example of them. If I did negative 6 divided by 3, this would be negative 2. Agreed? And the reason is because negative 6 is equal to, and I can put this 3 over here, 3 times negative 2. Sorry, I left my negative off. There. That's why, that's the answer, is that we're sort of inverting it, turning it into a multiplication problem. That's the definition of division. Now, we did a whole chapter. It wasn't a super long chapter, but chapter 4 was about divisibility, right? And it was about divisibility with whole numbers. But the reality is that divisibility with integers works the same way. So when we take a look at divisibility here with integers, we see again, it just draws us back into the same definitions we've seen before. A divided by b is a unique integer. If that happens, then a is divisible by b, or equivalently, b divides a. And we write the b with that vertical bar, that's our notation, and then a. And we read it left to right as b divides a. It's not a fraction, b over a. In fact, it's the opposite. It's a over b if you think about it fractionally. But it's b divides a. That's exactly how we defined it back in section 4.1. It's not any different. This is just saying that that idea extends to integers, just like we saw it with whole numbers. Our integer inequalities, again, looks just like it did with whole numbers back in chapter 3. For all integers a and b, a is less than b, written as follows, a less than b, if and only if there exists a positive integer k, such that a plus k is equal to b. And we've talked about this before. I'll do it with integers, like with some negatives here. So if I did negative 5 is less than negative 2, right? That's a statement that is true. It is less. The reason is because there is a number that I can add to negative 2, namely, negative 3, right? I don't think I wrote something right. That's what it is. I was like, I'm missing something. This should be a positive 3, but that's not right. You're right. I left off the minus. All right, thank you so much. So they're writing it as addition, though. Oh, because they wrote on the other side. Okay, let me reverse this. I was doing a subtraction statement. This is what I want, according to the way this is written. They're writing it as addition. The reason that this is going to hold, that this negative 5 is less than 2, is because that negative 5 can have something added to it. That number is 3. This number has to be positive. That 3 is positive, and it will equal the negative 2. I should say equals now. Sorry, I hope you're using a pencil. Most of you are. If you're not, I apologize. Still. All right, so there is a number that I can fill in the blank. I can add to the smaller number, and I can get the larger number. Right? And we've talked about this, not in this context, but I talked about heels. So I have a little 10-year-old. She's about to my shoulders now, right? So my little 10-year-old, if she wanted to be, she's shorter than me. So she's less than me in terms of her height. If she wanted, the reason I can say she's less than me is because if she were to step on a stair or a step stool and she were to increase her height by probably about 6 inches at this point would be all it would take, maybe less, I'm not sure, then we would be equal. Right? That's what it means, is that she can add something to the smaller value and it can make it equal to the larger value. And that's what this is describing in an inequality standpoint. And a little bit more of some inequalities. So theorem 5.9 says if you have an integer a and b, and a is less than b, or we can say b is greater than a, this will be true if and only if b minus a is a positive number. So I'll use the same example I did before. We'll see if I can get it written down properly this time. -5 is less than -2. Everybody agrees with that, right? What that means I have to be able to do is to take the larger number, that's my -2, and subtract off my smaller number, that's -5. So -2 minus -5. And this value will be positive when I'm done. And it is, right? Because we have minus a negative, this is plus, and so we end up with a 3. Sure enough, this is a positive number. So I'd have to be able to do the subtraction, larger number minus smaller number, and get a positive number in order for this statement to be true. And then theorem 5.10 talks about what happens with inequalities. And in particular, it's utilized a lot when students are first working with like solving inequalities. So kind of a pre-algebra-y kind of topic, probably encountered 7th grade math maybe. So the 6th to 7th, 8th grade, kind of depending on your level of the student and your curriculums that you're using. But it talks about how inequalities can be changed. So we have x and y and n, and they're any integers. And if I know that x is less than y, then it's also true that x plus n is less than y plus n. And that's true whether n is a positive number or a negative number, right? So if my little girl and I were standing up here side by side, right? And we both had on, I've got on a little bit of a heel right now. It's about 2 inches, maybe something like that. I'm not sure. We'll say 2 inches for the sake of argument. And she were wearing a pair of my shoes and she had on a 2-inch heel or a pair of her own, whatever. And we actually took off the 2-inch heel, right? That would be the equivalent of adding -2. Our difference would still be the same, right? She'd still be shorter than me, right? Or if we were both standing up here barefoot and then we both took a step on top of the desks, again, she'd still be shorter than me, right? So you add or you subtract a number. That's what the n's representing because it's positive or negative, and it will be the same. And so the second one, we don't need to do a second one that says minus n because n can be negative, okay? The second one talks about what happens when we multiply by a negative. So if I multiply by a negative number, do you remember what happens with inequalities? Yeah, the direction of the inequality flips. My 9th graders have been working with inequalities lately, obviously in a more advanced method than what's going on right here. But they struggle to remember sometimes when those negatives flip or when those signs flip. What has to do with the negatives? It's not subtracting a number, it's multiplying by a number, that kind of stuff. It's just, getting back into the habit of remembering the details. But I think it's worth noting why this works. And I'll use some simple numbers to do this with and not have to make it too complicated. But let's say that we had 3 and we know that 3 is less than 5. Everybody's good with that part, right? I'd like for us to put some negatives on them then. If I have -3 and -5, right? I've multiplied both sides by a negative. Think about why this direction changes. Why are we saying that -3 now is greater than -5? How would you justify that to the child? Why did that direction switch? It's closer to 0. And I think that's a good picture. We've talked about a number line picture. So when we were over here and we had 0 and we had 3 and we have 5, 3 is to the left of the 5 on the number line, correct? And if I write the other side of this, here's -3 and here's my -5 now, which one's to the left? Well, the -5 is. So the -5 is the smaller number because it is to the left on the number line. You could do it with chips and such too if you wanted to do it that way. But a number line gives a pretty good picture. This is the number line is what I was pushing back into with my children when I was trying to remind them why this happened. They didn't really care why it happened, by the way. But your more inquisitive younger kids are probably going to ask more whys than just sort of the rote memorization that my kids are interested in at this point right now with stuff, right? Yeah. Okay, we have a couple more. Let me see here. I'm going to move this up and smaller. All right, the next one talks about what happens when we multiply by a number, n. So they're separated because it matters. The first one says that n is now positive. So if you multiply by a positive number, what do you suppose happens to the inequality? Does it stay the same or does it switch? It stays the same. And again, we could use our same 3 and 5 if you would like and do an example. You can't prove things by example, but you can often get to the right idea by using a few examples. So if I took the 3 and the 5 and I multiplied them both by, say, 2, I'd get 6 and 10, right? The disparity would be different, right? But they would still have the same relationship on their which one's smaller. So it would be less than. But what happens if I multiply by a negative number? It flips. And this is just an extension of what we did, or a combination, if you will, of these last two, right? The second one here, x is less than y, and I multiply by negative, it switched to -1 specifically. Well, I could take that, and then I could multiply by the n that was positive, and I could see that if the n itself had been negative, I would have yielded the last one too. So it's kind of a combination of the last two pieces. And again, you could justify it with an example, take my 3 and my 5, and use a -2 instead, right? Now you'd have -6 on the left, you'd have -10 on the right, and the direction of your inequality would be switched, and you could justify with a number line from the same perspective. Okay, one last example. Well, it's got two parts to it, but example 5 is our last one, right? Okay, example number 5, it wants us to find integers that make each of the following true. So we can use some traditional algebra. You can use trial and error. There's not a one-size-fits-all. It has to be done this way, okay? So you have some justifications for this, but there are some things that might make it easier to do than others. And in particular, you might notice that both of these have to do with equalities, right? They both say equals. They could say less than or greater than and ask you a very similar question, right? And you would be looking for the same sorts of things. So as we're taking a look at this first one of the ways to do this, if you don't want to solve with algebra, which I'm not saying you can't, but I just want you to think about it from the perspective of a child who's not really worked that much with solving equations yet, is that you can identify the pieces that sort of match, right? They both have a -5 on each side. Well, what that means is that part in parentheses right here, this would have to be the number 1, because I can't multiply -5 by anything else and get back to -5. Does that make sense? So even without equations, we should be able to justify why the number, whatever it is in parentheses, has to be a 1. And then I can look and I say, okay, well, what does the x need to be in order to make that value -3 equal to 1? And the answer would be 4. So if we think about it like that, we would get a 4. If you want to solve it from a traditional algebra perspective, there's a couple options, and let me present both of those. Option number 1 is you can use the distributive property, which is probably the inclination that most of you would have if I gave you this question and just said, have at it. You'd probably have done it that way. You would have -5x plus 15 equals -5. You'd subtract 15. You'd have -5x. This is -20. You divide by -5, and you would get 4. This may be your inclination, but it is the most difficult way to do this problem from the 3 options I'm going to show you. I think the simplest one is the first way I showed you, but it does require you to sort of think about the properties and how they work, which might have a little bit of a higher level of thinking involved. The next option of how you could do this, which you might not have thought of, is to recognize this is multiplication by -5, right? And I could, instead of distributing it through, I could undo the multiplication by -5 by dividing by -5. So these cancel out because of it being division and multiplication being inverse operations. This leaves me with x minus 3 equals 1, and I can add my 3 to get x equal 4. Okay, so 3 different ways to do it. You can do trial and error if you wish. That's okay too. I'm not going to show you that, but you have an idea of how you would try that. You just try something, you see if it works. And if it works, great, you're good. And if it doesn't work, you try something else. Trial and error doesn't work quite as neatly if it asks you to find all integers that work, and there happens to be more than one, because you're kind of stuck going, well, like, okay, I found one. Is there more than that? This one, there is just one answer, and so you would be finished if you trial and error then found it was 4. Okay. Now, the next one is a really good example of one that even with algebra, distributing this all out with algebra is not pretty. However, you might look at this and say, hey, look, from an algebra perspective, I've got something squared on both sides. So I could square root this, right? I could square root this and see what happens and see from there. So we're going to give that a go as our first option. Obviously, trial and error is always an option. But then I'm going to talk to you sort of more abstractly about what's going on here and think about it from that perspective too. If we think about this by square rooting both sides as such, we would get this. Is that okay? Okay. The problem is that's not the only thing that we would get. So let's finish this out and I'll explain in a second. If I try to solve this then, I would add maybe an x to both sides. And I would have 2x minus 1 equals 1. And I'd add a 1 to the other side, and I'd get 2x is equal to 2, right, like that. And I divide by 2, and I would find that x is equal to 1. Now, if you look at this, you probably would agree that that's true. If I put the number 1 back in, 1 minus 1 is 0, so it's 0 squared is 0 on the left. And on the other side, also 1 minus 1 is 0, and 0 squared is 0. So this number works. This is not the only number that works, however. So I'd like for you to trial and error something for me real quick, and then we'll justify why it's happening and how we could have fixed it from an algebra standpoint too. Try x equal 3. On the left, we'd have 3 minus 1, which is 2. And 2 squared would be 4, right? On the right, 1 minus 3, which would be negative 2, but negative 2 squared would be 4, right? So on both sides, I think I said 2 a minute ago, I'm sorry. On both sides, I would get the same 4, but before I squared them, on one side I got positive 2, and on the other side I got negative 2. But why was it okay? Because I squared it, right? So square roots are tricky from an algebra standpoint, and you might remember some of these details as I'm starting to talk about them. Do you remember somewhere along the way somebody said if you put a square root into a problem, you have to put a plus or minus? This is why. Because negatives disappear when you square things, and they would in this problem as well. So from an algebra standpoint, the way that we would do this, which I'm not advocating the algebra standpoint, in fact, I'm telling you it's complicated, more so than you probably were thinking. We would do what we just did, where we square rooted both sides, but we would have to do an option down here that says, or I would have x minus 1 equals the opposite of 1 minus x. Because I could be getting a positive number on one side and a negative number on the other side. So the signs could be opposite from one another. I could have both sides equal to 0, or I could have one side 2 and the other side negative 2, and then square both of them and it still work. Here's what happens, though, when you do this. This is x minus 1 equals, I have negative 1 plus x when I distribute. And do you notice what happens on the two sides of the equation? Before we get to that point, what do you notice? They're the same. They're exactly the same. And again, in algebra, what you learn when things are exactly the same is that means x could be anything, right? So this actually tells me that x is any integer. So on this one, it's probably a little bit better to think about it from trial and error, to be honest. But again, don't just give yourself the pat on the back and find you're done when you realize something worked. Because what you should find if you trial and error something here is that you get the same number. I'm going to take my square roots off so we can go back and see this. So we did 3. So we found out 3 worked when we did it, right? And then we might try another number. Let's say we try 5. What's 5 minus 1? 4. Squared? 16. So I have 16 on the left. And then I have 1 minus 5, which is negative 4, which squared is 16. So if you try 2 or 3 things, you're probably going to start to recognize I'm getting the same number but opposite signs. And those signs don't end up mattering because I'm squaring it. And that's going to happen every single number I try. And it doesn't even work for just integers, although that's our focus and our what we're doing right now. It would work for fractions and decimals and stuff too. But I actually get any number to work here. Okay? So as you take a look at these, you will have opportunities too where you're going to do things with inequalities, and you're looking for that not just with equations.